So today it's a pleasure to have Jure Zupan from University of Cincinnati talking about flavor violating axions.
All right, thank you. Yeah. Well, it's a pleasure to visit, even though it's virtually. It would be nice to come to Minnesota once everything is settled in person. So this will be based on 3 papers. One is a bit older, so it's with Lorenzo, Calibi, Kurtz, Redigolo, Ziegler. And then the 2 newer one of them Maxime was on, so it's with Jorge Martin Kamalich, with Maxime, and Wong, who was an exchange student and is now a PhD student in France. And then the latest one, so it's sort of a similar crowd of people for all 3. All right, so the motivation here is really sort of very general. Like, we take a spontaneously broken global symmetry, we'll have a pseudo-Nambu-Goldstone boson. And the nice thing is, if this guy is light enough, it can be stable enough that it can be a dark matter candidate. And just from a bottom-up perspective, it will also have some couplings with, anything that is there in the standard model. So gluons, photons, or the fermions, with dimension 5 couplings. So this 1 over F will be the typical scale of the new physics where the spontaneous breaking happened. And the goal for this talk is to have a look at these couplings to fermions. And specifically, we'll be mostly interested in the flavor violating, so that the flavors of this I and J will not be the same. And we'll look at what you can say. So if you look at what the FCNC experiments are probing, is this at all interesting? And I'll also say a few words about how you could improve the search strategy in one case. So there's gonna be a few names floating around. So the convention is, whenever I talk about the axion or QCD axion, then the mass will come from the anomaly. Anything else that ends on ons, on any other on, like a flavon myron, will have an extra explicit breaking of the shift symmetry, which will be the mass. It's not a foolproof, this naming convention. So something that are called axiflaon or flaxion will be a QCD axion. So it's a bit of a mix as what people mean. But if you want to just keep in mind, now QCD axion will really mean you get the mass from the QCD anomaly. And then another thing that people like to use is axion-like particles or ALPs. This would fall into this category where you just put an extra mass term there. All right, so to just say this once again. So we'll be looking at the couplings to fermions, so leptons and quarks of an ALP, so a PNGB. And generically, you will have flavor violating coupling. So if this global symmetry.
May I ask you, usual axion has coupling only to gluons and maybe to photons, but you say that they also have direct couplings. These are direct couplings to fermions. So you introduce them by hand, right? They don't follow from usual arguments about axion, about Peccei-Quinn symmetry. They don't have direct couplings. These are our fermions, right? The fermions of our. So you just
fermions.
You couple axion to fermions by hand, right?
No, it's not by hand. So if you are a bit patient, I will go over the models as well. This first is bottom up.
If you
and then, there are 2 ways of doing it. I could start from the UV, I'm starting from the IR, and then we'll build up.
No, but in this way, whether this coupling breaks additional terms in axial anomaly or it doesn't, right? Because normally if you have flavor breaking, then you would think that corresponding axial current would be not conserved. The corresponding, I mean, symmetry would be broken, right? So that's why I think it's related to what Misha asking.
No,
related,
this is the coupling, derivative coupling of d mu a to any current that is gauge invariant is not, nothing is going to be broken.
No, it's not about gauge invariance. It's about, kind of existence of conserved axial current, right?
If
you neglect this kind of anomaly, the current should be conserved, right?
And it will be if you erase the coupling to GG dual, then you start with a massless axion, it will remain massless.
Yeah, it's what I'm asking, right? That in this way, coupling to fermions is such that is consistent with, kind of forget about say anomaly, right? That then without anomaly, it would be no coupling which are consistent with non-anomalous symmetry, right?
Correct. Yeah. So if you forget about the anomaly, there will be these couplings. No, so let's say this XFR would be the charges. These are the charges under the U1. The question is whether they are. I mean, if they are universal. Once you diagonalize, you don't have flavor violation. If they're not, then you have
right. Because I would be thinking
that's
that
all I want to say.
I would be thinking that if U1 is a good symmetry, then it's not flavor violating. That's why you see.
That's actually See, this is where I think let's say a prejudice comes in. You can postulate that it's not flavor violating. There's nothing wrong in charging different generations with different global UONs.
Okay,
in terms of popular UV completions, say Misha and Arkady Axion doesn't have this three-level.
Of course, yes. Your Axion doesn't have it, but it's very easy.
What is it called? DSVZ? No, DS.
DF. Yeah.
So it means that in certain way, Axion has a flavor, right? Because it's a couple flavor. So certain kind of flavor at least.
Oh, absolutely. Yeah. So I'll let's say maybe in 10 slides, I will do the extreme thing, where the U1 will be identified with the U1 horizontal that generates all the hierarchies. This I will call the axiflavon. So that's like it's really the U1 is the flavor.
No, but it's exactly what I'm asking about.
Good. Okay, I think we're. I should also point. So there will be more notation. So there will be this capital F appearing. It absorbs these couplings C in them. So if you want to think the decay constant, so the Axion decay constant is capital F if C is 2. All right, that's the convention.
But Yuri, I have a question here. Though. If you go back, sorry.
Back, yeah, sure.
Because I can always do a redefinition of my fermions, right? And so are you also choosing a basis here? How do I distinguish it? Like if I measure my CV, then what basis of fermion am I in? I can do I can do a rotation on the fermion.
Yeah, so from the bottom up, the best, like we're already below the electric symmetry breaking, so you really want to just think that I'm already in the mass basis when I write this. Yeah, but not when I write, so I'm a bit sloppy here now. So when I write this, you want to be, I mean, this is completely general basis, no? So, okay, I'm not sure what exactly you're asking me, but from the low energy point of view, the best thing is you just think of this as mass eigenstates already.
But can I do a chiral rotation on my fermions here and change these couplings?
Yes.
But they're already massive, probably.
Yeah. So here they're okay.
So you haven't chosen
the Z boson, right? So for the
the things will shift I mean, yeah, if you do a chiral rotation, I can move around. I can move things around.
Right, right, exactly.
And
That's my
I
point.
mean, I will generate GG tilde. I will generate WW. No, with, I mean, depends on what this chiral rotation is. So
Exactly.
I
So,
can shift.
so when you measure the CV here, right, it'll depend on what basis you're in, right? What chiral rotation you chose. So that means you would also need an independent measurement to say the axion to the gluon or to the photon to figure out what basis you're in. But you don't care about that, I guess, at this point.
Yeah. So yeah, exactly. So so what I did now is this is completely, we're in the IR, no? So I go in the basis where the mass matrix is diagonal,
Mm-hmm.
all the elements are positive, right? And I ask about the values of this C coupling, C over F.
Mm-hmm.
What are the bounds? No, so this will be like
But
part of the talk will be just about the bounds, and that's it.
But I'm sorry, following this, you already, when the UNR, your fermions are already massive, so there is no chiral rotation anymore. If you diagonalize masses, what kind of chiral rotation is possible?
So, well, I could, yeah, exactly. If I could still do it, no?
No,
could,
then
yeah.
your mass term is not diagonal. Diagonal. So in this way, you have a preferred basis where the mass is diagonal.
Absolutely, yeah. So I want to do the easiest thing, no? Like the nicest thing is I go to the mass basis. Absolutely, of course.
Yeah. No, but I also would like to comment.
Tony was not happy with my choice, so.
Yeah. No, but I'm trying to make a kind of, to use your motivation also to mention that it's a proper time to discuss flavor violation, right? Because of the COVID season.
Yeah, probably. Yeah. All right. Okay. So we're past the notation. So here's the outline. No? So I go over the bounds. Then I talk about this minimal oxyflavon. Then this will be for quarks, and then I'll talk about the leptons. There is a proposal for MEG II forward, which I will cover. And I'm almost 100% sure that unfortunately this I will just flip through the different models, but we can talk later. All right, so let's see. So this is from the paper with Maxime. So what we focused on the following. So we'll look at the QCD axion. So it will have a very small mass, essentially massless for the experimental purposes. And it solves, so it has this flavor violating couplings to quarks. So just to recap, now this guy can solve the strong CP problem, can be a cold dark matter candidate. And for me, the most important thing would be it's almost massless, very small mass that comes from the anomaly. So it's effectively massless in the flavor violating transitions. All right, so the strong CP problem is the following, that if I just write down all the dimension 4 Lorentz engaged invariant terms in the Lagrangian, there's a term that I can write, which is the GG tilde term, which along with so the theta term, the theta value itself is not observable, but this quantity theta plus the argument of the determinant of the quark mass matrices is. And the question here is, why is this theta bar measured to be below 10 to the minus 10 from the neutron EDM? And solution would be that theta bar is really a dynamical field. It has a potential at theta bar equals 0, so that you're driven to this CP invariant point. The mass is small in this case. It only comes from the QCD anomaly. So for these values of the Axion decay constant that will be interesting for us, this is sort of 10 to the minus 6 electron volts. And it's a viable dark matter candidate, let's say in this window, for the most vanilla case where it just comes from the oscillations. All right, so Now the upshot of what the constraints will look like. So what's plotted here is this capital F. So remember, this absorbs the coefficient of flavor violation. So if you think it's just order 1, this would be the decay constant. And there are a few things that are appearing. So it's a whole slew of different transitions. So S to D with a vector or an axial coupling. Then C to U with a vector and an axial coupling, B to D and B to S. And what is shown with a more bright color is the present bound. So the present bound on the S to D transition that is strongest comes from K to pi A. So that's a classic decay, decay, so the classic channel. And you see it's at the order of 10 to the 12 GeV. And this is the projected improvement in the sensitivity from Na62. Well, you can compare also the masses below. This is an effective mass. So I just plugged in this capital F in the mass formula, just roughly that we know what the mass would be. No? Of course, all the couplings would play there. Then what we see is interesting is all these other constraints. So I'll go over most of them and come back to this figure. One thing that you wanna maybe keep in mind is where SUPERNOVA 1987A is. There's a bound here, which is quite strong. All right, so I'll go over this quickly, what these different constraints were. So if it was a two-body meson decay that came from this flavor violating coupling, so let's say a pseudoscalar to a pseudoscalar like K to pi A, B to Ka, B to pi A, this would be sensitive to the vector coupling. And the interesting thing is that quite often the searches were not done by the experiments. For instance, for B to Ka, the search that is being done is really for B to K nu bar, so standard model decay, B to S nu bar, where the B to Ka would be the zero mass bin in the nu bar, right? So the Babar kept this bin, Bell actually cut it out. So there's no, for the full Bell data, there's no bound on B to Ka, unfortunately. Then for D to pi A, again, a two-body decay, there's no direct search. So what we had to do was recast the search for D to tau pi. So tau, so D to tau new search, where tau goes to a pion and a neutrino. And again, here it turns out that the Babar, so the recasting of Babar old measurements actually, oh sorry, Clio, it's Clio measurement is better than best 3. Still, even though the branching ratio measurement is actually better for D to tau new. If you have a decay to a vector, so let's say B to rho A, this would be sensitive to axial currents. However, there are no experimental searches that do this. It's a completely blind, I mean, nobody has done this, so that's an open field. I already showed, was pointing out these bounds. The two-body hyperon decays are sensitive both to axial and vector. And that's where the most stringent bounds on the axial, let's say SD coupling come from. I think I put the numbers. Or maybe I didn't. Anyway, so maybe the numbers themselves are not so interesting. The K to pi A would also be sensitive to this axial guy. And you could also attempt the three-body B to D decays. Here we go. So flash the lambda to NA. So what's these numbers that are not in the parentheses are the present bounds. And that's the improvement that you can aim for at best 3. Right. Okay, so it's essentially huge improvements because the searches are not there. So in many cases, you can really improve significantly.
So Jure, so right now, Look at that bound, which is 10 to the 6, say on the hyperon. If I take the decay constant as 10 to the 9, this would mean that the coupling CV would be like 1,000. Is that right?
Oh, so no, okay. So you're asking, I'm not sure what you're asking. So this is small
capital
f,
right? This is capital F, which is
so this
CV over the decay constant, right?
it's
sorry,
so it's FA over C.
CV,
yeah?
F over CV. So if F is 10 to the 9, right, you'll need CV to be of order 1,000 to be compatible.
Yes, or if it's 10 to the 12. But you see, this is, so what's in both phase is the most stringent constraint. Maybe I should go back now. It was, oops, sorry. So there's the most stringent constraint on this coupling is, so it should have said that both phase means it's the process that gives the best constraint right now.
Oh, okay, yeah.
So for the vector one, K to pi A will rule. It rules now, it will rule also in the future. And you're right, no, I mean, it's just dominated. If I go for the axial,
can you show how this F is defined? I mean,
yeah, absolutely.
Yeah.
This thing, no? So it's has this factor of 2 that we observed. Okay, there's FA and C. So C equal to 2 is capital F is equal to FA. Right?
I see.
And there's also an F without this V and A, where C equal A, no, 1. In that case, this capital F is small fa.
I see. So it means that, you know, this C is inverse to F, right? I mean, this coefficient coupling are inverse to thanks to the amplitude of F. No, okay.
But no,
if you have small c, means you have to have a much bigger sensitivity.
Yeah. No, it was the way I was thinking, but just to verify.
No, but if the limit on capital F is less than 10 to the 9, then the CV has to be much bigger than 1. That's
I see.
Yeah, if you want this to be to 10 to the 12.
Yeah.
Exactly. Yeah.
Absolutely. Yeah.
Okay.
Yeah. So that's
Thanks.
why. I mean, at some point I'll have both diagonal and off diagonal on one slide, and then maybe we can say this again. All right. So I think we're here. So maybe an interesting thing is to compare this with the bounds that you would get from the MESON mixing, so like a classic FCNC observable. So what you can do here is, so for KK bar mixing, you can use chi-pt, and then the BB bar mixing or DD bar mixing, it's a very simple operator product expansion. So there's a positive and a negative side of doing this. So it's nice that it doesn't depend on an ALP decay mode. So if this was not a QCD Axion, but something a bit more massive, all the searches that are in the decays would depend on what this ALP decays to. Well, either it's invisible or decays to 2 photons or 2 electrons and so on, displaced or not displaced. So this is gone, no? Because I just depend on the SD couplings. However, the bounds are UV sensitive, no? Because the insertion of Axion will have the same parametric dependence of 1 over F squared as any other dimension 6 UV operator. So you have to just say that these are smaller than the Axion contribution, all right? Which is may or may not be true.
No,
but it's still interesting to.
But it gives you some kind of limits to which bound you can go, right? Because you cannot go better than this, right? I mean,
yeah, I'm not sure what you mean, but
no, but because of this mixing, when you are looking for this flavor breaking, then I think that then it's limited by this existing mixing, right? Because I mean, it would limit your possibility to put limits, right?
So yeah, so there you just, so maybe I didn't say this clearly enough. So, but okay, let me go over this slide and I will say it again.
Okay.
There, what the approximations are. Maybe it will be clear. All right. So let's say for KAON mixing, the KPT would organize all the terms for you. So the three-level exchange of Axion would be order p squared, and then there's order p to the 4 terms that come from one loop exchanges. This has, since this would be an axial coupling, and if we look at the mixing matrix, so the M12, you see that there's an FA, F capital A appearing here. So it's because this guy is a pseudoscalar. And if you didn't use KPT, what was done, I mean, it's 20 years ago, was just a vacuum insertion approximation. This one would be 5, 6. So what we did is not a big numerical change, really. Mm-hmm. And then there is these corrections here. Okay, so what are the approximations in the bounds that I'm showing, or we derived from mixing? So there are 2. The first one is that at order p to the 4, there are these counter terms, just the KPT counter terms, that are not known, because now I have a light degree of freedom that changes the values of these couplings. So we set them to 0. So it just means it's a, this doesn't matter much numerically because it's just an NLO piece, but for the vector couplings, these are coming from the order p to the 4 for the first time. This is a big approximation. No? It's like an order 100% error, no? on the bound. You could easily shift by 100%. So that's approximation number 1, is just knowing the QCD with this axion. The approximation number 2 is that, so this, you see M12 goes as 1 over the UV scale squared. It's really a dimension 6 contribution. So any other dimension 6 contribution that comes from the UV can shift M12 in the same, by the same size. So we just ignore those UV contributions when we derive the numbers, the bounds. So these are the 2 approximations. Did it answer what you were asking?
No. I was wondering.
Not really.
Whether this flavor violation, flavor mixing, of KAON influence to other, to limitation which you are using from the decay, because in the decay you are implying that it is particular flavor there, right? I mean, and if there is a mixing there as well, for mesonic mixing, right? Then would it change those limits?
Yeah. Oh, that's very good. Now I understand. Yeah. So this. Yeah. So the bounds that come from the decay are much more stringent than the mixing ones. So if you look at the decay, let's say there was some k short doing something, pi to a, you can completely ignore the mixing.
I see. It's what
correction to the mixing. Yeah.
Yeah, I understood this. Yeah. But okay. But in terms of kind of formulation, this kind of axioms that essentially when you are discussing here, when in this particular slide, I would call it mixing between K and axion, right? It's not because just iteration of this, but the fundamental point it is what is the value of mixing between K and A, right? That's it.
Yeah, absolutely. It's correct. This is I mean, this is calculated in the mass insertion approximation, if you want. It's a mixing between K and A, absolutely.
Yeah, right. And then it's like iteration of effective Lagrangian. Once you have this mixing, you can calculate the amplitude, right? But it's not. I mean, the interesting part is just the mixing itself.
Yes, the size. I agree. Yeah, I think. All right. So this was. So that's okay. So maybe just numerically, the epsilon k. Gives the best bound on the CP violating part with these caveats. So it doesn't come from the decay, but with these caveats, it would come from here. So you can do a similar thing for the heavy meson mixing. where okay, I mean, the momentum flowing here is well above the QCD if this is the B quark line. So you can just do on 1 over MB expansion and match onto the dimension 6 operators. So here it's important for the CU-A couplings, assuming that the charm is much heavier than the lambda QCD. Otherwise, it's completely irrelevant. I'm not even showing the numbers. So there was this supernova bound that I also showed. This was kind of interesting, is that in the neutron stars, the lambdas are in equilibrium with the neutron, proton, and the electron. And then what can happen is that you could have a lambda to neutron plus an axion decay. And this process would cool the star, the proto-neutron star, because axion would escape. So what you need to do is one needs to take into effect the Pauli blocking. For instance, if the temperature was 0, then this decays would be forbidden. You can decay into a full Fermi C. However, at finite temperature, this is lifted. And if I just show the non-relativistic limit, ignoring this Pauli blocking, the emission per volume would be the following. So you have the energy that is emitted, so lambda mass minus the neutron mass, then the number density of these guys that we have around, the decay width, and then there's the temperature suppression, right? And this, so this very simple thing agrees with the Pauli blocking expressions within, let's say, 40 or 50%. Now, the next step is that assuming that the supernova 1987A as the standard, it's a standard supernova explosion. From the observation that there's no nothing funny going with the tail of the neutrinos, you assume that this cooling is less than the neutrino cooling, and this would give you a bound which is at 10 to the 9 or 10 to the 10 GeV. It depends quite crucially on what you plug in for the temperature. No? So shifting this from 20 to 40 MeV can shift Q by 2 orders of magnitude. All right, oops, where we are. Okay, so that's, I went maybe quickly over these bounds. And what I didn't mention is the comparison with the couplings that are diagonal. So what's shown here as these diagonal lines is the white dwarf cooling bound on the coupling of axion to electrons. Then there's the supernova 1987A coupling, so this diagonal coupling. This is the FN. And then I also plotted the cast bound on the photon coupling. I mean, this is for certain windows of axion mass, the bound on the photon can be much, much more stringent than this cast one, but it's still a good thing to show.
Okay.
So the thing,
I'm sorry, step aside a little bit, because returning back to this mixing, I mean, between, say, pseudoscalar meson, for example, and Axion, I would say that in the chiral limit, I would be thinking that all this kind of flavor change decay could be interpreted as just, you know, kind of Fermi, I mean, this, instead of this coupling to Fermi, I would say that it is this decay, it is just, say, I don't know, say Xi goes to sigma and pi, and then pi decays, pi mixes with A, right, with Axion. And because of small masses of you know pseudo-Galsol, I mean pions or KAON, I would say that it is a dominant contribution. Then this limit would be like a limit on the same mixing, right? I mean between meson and A, and I do not see why this chiral limit could not be applied to what you are doing.
Yeah, so you're asking me about the bounds on the pi A mixing?
No, you already discussed. You
Yeah.
already discussed this mixing, right? I mean, this mixing does exist. What I'm trying to say, it's more that if I'm discussing this flavor change decay, then I could reinterpret this decay as decay to pseudoscalar meson, and then I mean with the production of scalar meson, which then mixes with A, right? And this contribution would be everywhere.
Yeah, okay.
Sure,
I think
Kelly, because this mixing is basically a kinetic mixing often, right? So it's a d mu pi times or d mu k times d mu axion, right?
Okay.
When you put the axion on the mass shell, then the effect of that mixing is going to be small. However, there is a direct, say, matrix element between a hyperon and the nucleon because of the SD current that axion couples.
But you mean that the mixing would be suppressed because
by the mass of the A, yes, because it's a kinetic mixing, right? I mean, like you discussing like the diagram, like sigma goes to virtual K, right?
Right.
Virtual K mixes with an axion and continues as an axion, right?
Right. It's what I'm asking. Yeah, indeed.
Yeah.
But I thought that, for example, for normal axion, this mixing with pi was a kind of a dominant stuff, right? Because of my.
Yeah. Oh, yeah. Okay. Now I think now you're asking. Yeah, but if you have a direct SD current.
Yeah.
Like if I remember, so using. So if you use the standard model W flavor changing, I think it's about, the difference is 6-7 orders of magnitude on the bound on F, something like this. I don't remember the exact numbers. So this would be much less constraining. Just because it comes from, you have to, so you have to, you're paying the price from the W exchange, which suppresses it significantly compared to this.
No, right, but because it depends what kind of flavor. No, but if you had originally, yeah, I understand that. But say this when you're discussing this derivative coupling of axion with fermion, what I am suggesting that you can just substitute this axial current of fermion by corresponding d mu meson, right? D mu acting on meson, right? Okay, so in this way it would be a model for matrix element of this fermions, right?
But it will be small, right? Because
I got your point. Yeah, I understand. Yeah, but it but it is kind of. The point is that this would be singular in the meson mass in the limit of chiral symmetry.
So I think there are sort of.
I agree with that. Yes.
Yeah.
Okay. Good.
Yeah.
Right.
Yeah. Okay. So sorry to interrupt, but just.
No, it's okay. Yeah, it's good.
Sorry, Jure.
Yeah.
Jure, what is the underlying assumption between the translation between FA and to those diagonal couplings, the capital F? You introduced.
Yeah. Very good. Yes. Yeah. So here, all these C's everywhere were set to 1.
The C's for the diagonal couplings you assume to be.
Yeah, they were set to 1. So whenever you see.
Yeah, but for the off-diagonal ones,
it's also every C in this plot is set to 1.
Okay, both diagonal and the off-diagonal ones.
Yeah. Every C, I, J, A, and V are set to 1. And then you convert. I mean, it's really what's plotted is capital Fi. No? So, but if you want to think the conversion to the same small fa, you just set everything to 1, to 2, in our notation.
Sure.
Then this Fi is the Axion decay constant.
Okay.
And maybe just once, so if I go back to Tony's thing where he wanted to divide by 1,000, no? So you compare the coupling to the electron, you see that the off diagonal C is 10 to the minus 3 or so. You are roughly where the white dwarf cooling bounds are. So anything that has an off diagonal S decoupling that is bigger than 10 to the minus 3, the dominant constraint is from K to pi A. It's another way of saying this. Okay.
Yeah, but maybe let me ask a follow up on that. What set up your basic, maybe two aspects. One is, don't I generically expect the off diagonal ones to be smaller than the diagonal ones? Maybe that's a model that's based upon your own like flavor, like kind of anticipation. The other things, the choices in your earlier ones, when Tony asked the question of C for off diagonal being 1,000, sounds, where does the 1,000 come from? Like when you list that on your table.
This you have to ask Tony what he had in mind.
No, I mean, I just wanted to know just the rough order of magnitude of the C, because indeed, if you take the decay constant to be 10 to the 9, then you'll need a theory that gives you C of order 1,000. But no, I mean, you're just getting model independent limits here, so that's fine. I mean,
right.
At this point, but eventually you will have to. I mean, you're going to talk about models, right? Where you can.
Yeah, so that's the next thing that I wanted to do.
Yeah, because you're going to estimate typical C's in models, right?
Yeah,
and
absolutely. So yeah. I just want to. So we're almost 45 minutes. So so when should I finish?
No, I would say, yeah, just go ahead. We can do a brief pause in 1 hour in case people have to leave and they want to ask questions, but otherwise we're. Yeah.
Okay. All right. So what I do next is, I think what Jen just asked me, to give him a model, so we can think about the correlations between different different couplings. So here I'll do the extreme version, which is that I'll identify the Frogant-Nielsen U1, so the horizontal U1, with the Peccei-Quinn symmetry. So what's shown here now is let's say I have so the assumption is that I have the expansion parameter, which will be the flavon wave over the mass of these vector-like fermions. These are these wavy lines. So this wave over the mass of the fermion is an epsilon. This epsilon would be maybe 0.2. So there's a factor of 5 ratio between the wave and the mass. And the standard model fermions are charged under this horizontal U1. So so just looking at the low energy, I need to have a spurion sitting in front of a Yukawa term that makes the whole thing U1 symmetric. And this Xij's will be the relative differences, so the differences between the two charges. So if I have T right and Q left, if they have a very disparate U1 charges, this will be a long chain, and this will be a hugely suppressed mass term, Yukawa term, right? So the ingredients are there, no? So I need a global Peccei-Quinn symmetry. That's the horizontal U1. It is spontaneously broken, so I have a PNGB, and it is anomalous under the QCD. So if I do this, I identify the Frogant-Nielsen U1. You can explain the QCD, the strong CP problem, and the flavon. So this axial guy. So the face of the flavon field, so phi has a wave, there's a radial mode and the axial mode. This guy is the QCD axion. And the couplings to the standard model fermions are now controlled by the standard model, the values of the standard model Yukawa. So this flavor off diagonal guy will have a parametric site, which is just the geometric mean of the masses. So the off diagonals will be this geometric mean of the Yukawas. It all depends on still some order one numbers that were floating around in the setup that were not fixed by the symmetry. So in addition to these flavor diagonal couplings to electrons, nucleons, photons, and gluons, we also have this flavor off diagonal guys. So now I lumped everything on one slide. This is the mass of the axion. This is the coupling to photons. These are different constraints that are coming from flavor diagonal coupling. So this is the correspondence here. No, it's just grayed out. It's a 4-year-old plot, no, so not everything is up to date. These dashed lines were the projections for different experiments at that point. The blue line, that's the interesting one for the flavor piece. So this is just a bound on FA, so it's really just a bound on MA. So bigger FA means smaller masses, so everything to the right is excluded in this case, and it's coming from these old bounds on the K plus 2 pi A search. While the projection for Na62 is this dashed line. And it's also nice to plot this window where you would get a natural axion as a dark matter window. So this theta is would be the value of the theta parameter, so theta bar at where you had to start oscillations in order to get the relic abundance that we observe. So this is 1, 10 to the minus 1, so and so on. Depends on how much tuning you allow, the further to the left you go. So with this, in this Axi-Flavon setup, we're just starting to probe the dark matter region. Okay, all right. So I will switch gears now and I'll start talking about the leptons. And here will be a slightly different setup. So it will be, so the first part will be again bottom up. I will assume that the lepton, the couplings to leptons dominate, but I will also allow for non-zero, so varying ALP masses. So the masses will not necessarily be coming from the QCD anomaly, but I will allow for a variation. There will be a limit where I also do this. All right, so the main question here is we have these facilities that are that will have 10 to the 15 to 10 to the 17 muons produced, MEG II, MEG-II, MEG-III, MEG-IIe. What does this? What can this bias compare to what was measured, where 10 to the 7 roughly muons were used for bounds on the Axion coupling. So there's an old one from 86 and a newer measurement from Twist in 2015. But you see, it's really an incredible gain in muons that these other facilities will use. So can we do something new? So the upshot of what I will show you is shown here. So that's the mass of the ALP. So this is 10 to the 2 electron volts. This is the GeV here.
So it's no longer the QCD mass, right? QCD induced.
Yeah, exactly. So depends where we end, but I also have a QCD Axion version of this. So it's just, there's an extra shift breaking parameter that I allow the mass, and we just ask for what the bounds are. So these are the astrophysics bounds, white dwarf cooling, red giant cooling, the supernova. Bounds are coming from the flavor diagonal ones. So again, setting the C's to be just 1. you can compare with what you have, for instance, at present. This is this UDDO bound. There, I will go over different different shadings, but this, you want to compare the solid lines with the projected new bounds that you can get at MEG II forward and MEGII-3 online. All right, so
Well,
let me
is it
explain this figure.
Is it obvious that, that you get better sensitivity through these PSI things or from maybe muon beam stops at Fermilab, where you have you try to detect the displaced decays by
yeah, the displaced decays are here.
We can't see the pointer for some reason.
Oh, you can't see the pointer. All right, so it's
No.
the, oh, that's very bad. All right, so I'm not sure what I can do, but there's C tau A less than 1 meter is this lower left, so lower right bottom corner.
Okay.
This is where you start getting the displaced guy. All the rest that is not colored is it flies out, so it's invisible. Yeah.
Missing energy.
You're missing energy, yeah.
And what's supernova 1997 AMU?
Yeah, so it assumes that you only couple to muons.
To mu, okay.
Yeah. It's very bad that you don't see my pointer. Okay. All right, so I'll try to say where I am. So there are two types of searches that were done. There's option one is you try to suppress the standard model background, which comes from mu to e nu bar. And this is this 30-plus-year-old experiment at Triumph. So they used polarized muons. The polarization is plotted here. So it's polarized in the opposite direction that the muon flies. So this is this plot to the left. And if you look at the positron in the forward region, so this would be in this dashed line, theta E is the angle that this positron is, the opening angle for the positron. And what's plotted here is for different to the right. The plot to the right has different choices for values of theta E. The solid line is theta E equals 0, cosine theta equal 1. And then you slowly go away from the forward region. You see that if you go completely forward, so Xe is the energy in the positron. So if you go at the endpoint, that's the positron momentum divided by the muon. If you're at the endpoint where Xe is equal to 1, there is no standard model background in the exactly forward region for a fully polarized muon. And this is where the decay to a QCD axion would pop up. So if you have a massless axion, you would see a bump at Xe equal 1. So that's the strategy, is that you use this suppressed standard model background to search for a line at the very end point. So that's your DDO et al. The problem is that you are only sensitive to right-handed couplings. So the left-handed couplings have exactly the same behavior as the standard model background. The option number 2 is you don't suppress the standard model, and you just look at so unpolarized muons, and then you have to deal with the bigger standard model background, but you are sensitive also to left-handed ALPs. So that's the twist measurement. All right, so here's our proposal for what MEG II could do. They also have polarized beams. You could repurpose the detector and for the mu to EA search. So we call this MEG II forward. And what you need to do is you need to place an ecal downstream from the target. So this is what's plotted here. Is the target is where this red point is, and then 1.5 meters there is a there's a nice spot where you could put an ECAR. And the bounds that I will show were obtained with a 10 centimeter LISO ECAR. So pictorially, there's
Sorry.
already radioactive.
You
Okay.
mean which target? The target where they produce muons, or the target where they stop muons after a beam?
Oh, where they stop muons, sorry. It's the stopping point.
Okay.
Absolutely, thanks for that. Yeah, so you see this on this figure that I just showed, is this red blob, is the muon stopping target. To the left is where you want to put the LISO calorimeter. So there's already a decay counter there. You could replace it with a different calorimeter that would count also more energetic positrons. So far, it sounds like a very small change. The real difficulty is that you also need to do something with the magnetic field. And that's where, so we just did the very naive thing, is that you completely switch off this thing. So that's the bounds which are plotted with no magnetic focusing, so F equal 1. Or what was achieved is you arrange the magnetic field such that it focuses the positrons toward this LISO calorimeter, and F of 100 is something that this Uddio et al. From 86 achieved. And the plots are with 2 weeks of running. So these plots here, now I can go over. No, so the Uddio et al. From 86 is the green line, and there are the assumptions are the solid line is that the axial and vector couplings are the same, equal to 1. The dashed line, which is above it, is that you have only right-handed coupling. The dashed green line, which is way below, is left-handed coupling. And you want to compare the solid one green line with the MEG II forward, let's say no focusing, is F equal 1. That's after 2 weeks of MEG II forward. And then there is F100 is the orange thing.
So your signal is just the energy of the positron?
Yes. So if you're anywhere below, let's say 10 to the 7 electron volts, you are basically at the end point. You can't resolve that. This once the mass of the ALP is above 10 to the 7, you start shifting away from the end point, and then it degrades.
So if you have some pi plus contamination of your mu plus beam, that should create a background, right? Through pi to
yes,
neutrino decays, which they do have pions in that line as well.
Yeah. So again, this is Fino's dream interpretation. So what we're trying to do now is, Angela Papa is involved for the contributed paper for SNOMED. So we want to do a much more realistic estimate of the backgrounds. So we'll see. But yeah.
Why do you need to turn off the magnetic field? Maybe I missed that part.
The magnetic field right now is configured such that you, it's for a mu2e gamma search. Okay. So you have so this configuration is such that you have positrons rotating around in this magnetic field to reduce the background from for the photon search.
Mm-hmm. Mm-hmm. Why couldn't you place your detector somewhere else instead of the forward direction?
The forward direction is because you want to reduce the standard model background. So that's physics. No, you already have a polarized beam.
But are you saying just that if you place somewhere else to follow the lines, so that if it comes out forward in the physical process, but it ends up in your detector after propagating through the magnetic field, you're saying that then in that configuration, you'll probably have a lot of backgrounds? Is that what it is?
No, okay. I mean, you could, it's not going to be axially symmetric, what you're proposing. but you could try to do that. It sounds more complicated to me, but you know, I don't know. It's just this F equal 1 was no focusing, and what happens to the backgrounds, God knows, no? It's really you know, okay, it's a propaganda plot. Now, is you want to know how well you could do with very simple assumptions. A more realistic thing is really, you know, now that we got experimentalists involved, it's going to be more realistic, I think. And we talk to them, but it's not the same.
Okay, thanks.
Yeah. All right, and then there's MEGII-3E. So they can do a similar thing. No, they just search for a positron. They bin all the positrons that they have, and then they try to find the peak on the background, on the slowly sloping background. There are some details there. They can't use, I mean, there's so much data, they can't really use all the tracks, actually. It's some short tracks that they need to use. But the reach is quite good. No, you see, it was comparable to this, or slightly better than MEG II forward. And I think the interesting thing is the projected timeline, because MEG II forward would be at the end of MEG II run, probably. You don't want to mess up with the detector before, probably. And this is where MEGII-3E phase 1 would start running, presumably. But a lot of people are on the same experiment, so okay, I don't know. So it's sort of, I think the whole timeline maybe makes sense to do both. There's also ALPs in taus, where BEL2 can do a search. I don't really have much to say here. All right. So I talked about, maybe I talked a bit about the astrophysics bounds. I will skip the details. Maybe I have maybe too many slides. Clearly I have too many slides. So maybe, I don't know what's best to do. Maybe I'll go very quickly over the models. So I have one more plot where I will say exactly what I have on this slide, which is that if you ask about the dark matter, this is couplings to photons. This part is excluded, and depending on what you assume for the, oh, you can't see my pointer. So these dashed lines are where you would get the relic abundance, depending on what you assume that is happening with the potential. So either it's the T equals 0, or you assume like a QCD, like temperature dependence. So these are the two dashed lines. And you see that in some regions, you touch with experimental sensitivity, which is interesting. That's what I wanted to say here. All right, so I have 4 LFV ALP models. I will maybe just go super quickly over what we looked at, and maybe in the question session you can ask me more. So I'll just go maybe very, very, very quickly. So the 4 are lepton flavor violating QCD Axion. Then there's the Axi flavor version with the lepton flavor violation, leptonic famulon, and the myoron. And here, so the first one is a QCD Axion. It's the DFZ-like model where you have their flavor. So they are the charges. The U1 PQ is flavor sensitive, so you charge non-universally in the leptonic sector. So sorry, I have to flip forward. And maybe the interesting thing here is that you rule out quite a big chunk with wide dwarf cooling. So everything to the right on the left plot. Okay, it's really bad that you can see my pointer. So there's these orange lines that you want to look at on the plot to the left. There's one particular choice for how the 1-2 mixing looks like. And the future are the dashed lines, these vertical dashed lines, MEG II forward and MEG II 3E. There will be a big change in, there's a significant change in the sensitivity above the astrophysics lines.
So Yuri, so
and
this,
there's, oh, yeah.
for that particular model, you're not solving the lepton hierarchy, mass hierarchy here. You're just trying to generate
yes,
a
absolutely. Yeah, absolutely. So the story here is you assume a PQ symmetry, which is flavor non-diagonal, but the flavor structure itself for the UPSHOT is external to it.
Yeah, because you're taking universal PQ charges, basically. Is that right?
Yeah.
Yeah. Okay.
Yeah, absolutely.
Yeah. Okay.
But,
Yeah, it was this colorful thing.
Okay, could it be then? I do not see why you should be limited by one axion, right? It could be that you have, kind of non-abelian type of symmetry, right?
Yes.
Like
yeah. Oh, I'm so happy. It's the next one. The next one. Yeah. Yeah. So yeah, of course, there are many choices here. No, it's not. We just so I think the game here was. All right. The goal was really to have axions that couple mostly to leptons, and that you have large flavor violating lepton, so flavor violating leptonic couplings. And the models are, some are ugly, some are more realistic. So I think this LFV axi flavor is actually not so bad. What you have here is the PQ symmetry is part of this SU2 cross U1 flavor group. And what you need to assume that the ugly part is that this there have to be two breakings, one for the quark and one for the lepton sector. And so the FA for the quarks needs to be higher. Then you have mostly couplings to the leptons. But the fact that the flavor violating couplings for the leptons are bigger actually does not depend on this. It's just the structure which is already built into the SU2. It's because you always have to go to the third generation to have these flavor violating couplings, and you pay a much bigger price in the mixing than actually I think I mixed up stuff. So I will backtrack now. I was talking about two things. It's SU2 cross U1, and it's really just the flavor violating K2 pi coupling is suppressed because of the small mixings that are generated in the quark sector, but not in the leptonic sector. Right. So here naturally you will start seeing mu2 EA before you're seeing K2 pi A, and that's what's shown on this plot. So these are all the constraints from flavor. And the K2 pi A doesn't even feature. The red lines here are so the mu2 EA present is this dashed line. mu2 3E future is another dashed line much further, so further to the left, so even further than the wide dwarf cooling. And K2 pi A would be to the right, so it's not in this plot at all. Yeah, sorry. So so the leptonic famulon is the other example where it's just the Froggen-Nielsen U1, and I have two scales. So leptonic scale is much lighter than the quark one. So it's an oxyflavon, but where you see the flavor violation in the leptonic sector. And it depends what you assume for the charges, you'll have different relative sizes of left-handed and right-handed couplings. So that's the orange lines move depending on what the assumed flavor structure was. And finally, this Myron, you rely on the same trick as the low energy seesaw people are, which is that the neutrino masses have this Y-Y transpose structure, while the Myron couplings are YU dagger, so YU dagger. So if there's any global U1 symmetry, the neutrino masses will be suppressed by this global symmetry, while the Myron couplings are not. So you can have significant couplings, and that's what's plotted here. So
Right.
again, mu2 okay. So this is the last slide. So I went super quickly, I'm sorry, but I guess it's the nature of these Zoom talks is different. So conclusions. So FCSCs.
In the Myron case, you have no bounds from the neutrino sector. Is that the statement, or?
What specifically were you referring to? So
in the plot that you had, I was just wondering what the most important bounds are. I guess
right
these
now
are just couplings to
cooling.
charged leptons. Okay.
Yeah, there's a belt to tau to mu A search, which will become here relevant here. There's an Argus tau to mu A, tau to EA search, which is here. The neutrino masses are completely suppressed here. So,
okay.
Yeah. All right, so I talked about the FCNCs to search for axions. So there were sort of maybe two messages here. One, which was interesting, was that this type of searches fell by the wayside for in the quark flavor community. Many of the BSM searches were not done, but could have been done, like B2KA, B2K star A, D2 pi A, and so on. And then I advocated for this MEG II forward phase of the MEG II experiment, where the interesting thing is that you can go quite well above the previous experiments and the astrophysics bounds. Right.
Okay. So maybe we can thank Jure with our virtual applause. Click the button there. If there are any questions.
Yeah, so I just have a question about these models, these lepton flavor violating models that you mentioned at the end. Is it fair to say then that if you also try to explain the Yukawa coupling hierarchy, then the bounds that you get are just much weaker than, say, the astrophysics bounds?
Yeah, so that's a good point. Now, so there are the two cases that where you were explaining flavor and had a QCD axion at the same time were these two guys, no? Was this LFV Axi-flavon, where the PQ is really embedded in the flavor symmetry, and then the bounds were this, no? So you see that this grayed out stuff is the searches for the axions, right?
Yeah.
And then where the mu2EA present is worse than the white dwarf cooling, which is this red stuff.
I see.
But you have quite a good shot at pushing above this. So yeah, so for this particular case, it's the right-handed couplings that are more important. So the MEG II forward would not really probe this scenario well.
But is this just
a 3E would, yeah.
Yeah, sorry, is this just a generic problem in the sense that if you're trying to explain the Yukawa coupling hierarchy, then that eventually feeds into the off-diagonal couplings, right? And makes them small.
Yeah, the question is how small, no? And exactly, no, I mean, that's what you always expect, no? Is that you want,
Yeah,
you
because
won't end up with just order one stuff, no?
yeah, because it looks like
Right.
now the experiments are probing, you know, couplings of order 1, but that's incompatible with, say, explaining a Yukawa coupling hierarchy where you expect those couplings to be actually much smaller than 1. Is that a fair statement?
Yeah, yeah, I think, yeah, it's a, I mean, what you would typically expect is that you'll end up with some, well, it's not always, no, but sort of the naive guess is you just have the geometric mean of the, of the diagonals would be the off diagonal, no? I mean, it could be larger, it could be smaller. And in this, so let's say like here, it really depends on what you, so that's this leptonic famulon. So you just think of U1 for the leptonic sector, no? And the quarks have a different U1 that has its own Froggatt-Nielsen. And here it depends on what you assume for the neutrino masses, no? So that's, they would come from the Weinberg operator, pure anarchy, which is perfectly fine with what we see, no? Is this, all the charges are the same, or you can plug in some hierarchy for the neutrino masses also. All right, so these are the two things that are plotted there. Just a second, maybe. And you see that, you see where you would be, no? So you have a shot, anarchical famulon is a bit worse than this hierarchical one where you can go well above the cooling point.
I see.
Yeah. And so this is sort of in a concrete model. Now you see how bad this, like if you want to explain both, how bad this is. Yeah. There was a question.
I that maybe kind of maybe I do not understand this particular point, that when you talk, for example, you mentioned something like a horizontal symmetry, right, between different flavors. But when you have this kind of spontaneous breaking of horizontal symmetry, you could think about terms of, say, Galson bosons, which are kind of not just one, right? But it would be like you know, like multiplet of this horizontal symmetry, right? Then you would have some number of those kind of axions or whatever, right? And maybe I'm getting this wrong, but my impression was that you are always implying that it is one is the same axion, right?
I was doing the simplest thing. You're absolutely right. There could be many more.
Yeah.
I mean, like there is a simple way. Yeah, I mean, there's actually it's a nice way of writing these Froggatt-Nielsen models.
Yeah.
Where you would have two flavons, right? And all the masses would come from the waves of these flavons. Also for the vector light, what you see is the vector light guys. No?
Okay.
Yeah, and in that case, all right, you could have, so in that case, you only end up with one axion, but you could do 3 flavons, then you'll have 2 axions actually.
Yeah, right. It's what
absolutely.
I meant that, yeah.
Absolutely, yeah.
Right, but so it should be some kind of, I don't know, some kind of beauty in the model, right? I mean, to have a preference why you would consider this, because otherwise it's too many possibilities, right, to consider. I mean.
Yeah, absolutely. So I think both of these papers are really so the first one definitely, is absolutely just written from bottom up. Then this oxyflavon, the simplest one, I mean, that's really driven by beauty, if you want. No, you identify, I mean, there's one U1, you identify this that solves both the flavor and the QCD, the strong CP problem. And then there's not much wiggle room. Now, if you go for this minimal setup, there are order one factors that fly around, but they only change things logarithmically. So maybe if I go back now, there was a very, so this is, I had this band, maybe I didn't stress much. So this is the Peccei-Quinn band, where all the couplings were varied between 1/3 and 1/3, where with the symmetry you would say it's order one. And there are quite a few couplings that, you know, all these vector-like fermions have assumed masses to be at, let's say, F, no? Or 1 over epsilon times F. And you vary all those masses on all the off-diagonals. And you see that it's really a very small change in the end. Yeah.
Okay, thanks.
Yeah. Mm-hmm.
More questions?
Hi, Jure. Thanks for a nice talk. So is it fair to say that in the common discussion of Axion phenomenology or Axion-like particle phenomenology, people often drop the Yukawa type of couplings, and but your talk uniquely covered those discussion. The question is that true? And why did people often don't consider those Yukawa type of couplings? From your point of view?
Okay, it's a good question. For couplings to electrons, certainly not.
Yeah,
I mean this.
Sure. Except for with some particular exceptions. Yeah.
Yeah. And then probably part of it is experiment driven. There are many more ways to probe photon axion couplings than, let's say, the couplings of axions to protons and neutrons, which could come from GG tilde, or they could come directly from UU bar DD bar coupling. I mean, just see. So that's this Casper idea. Why somehow couplings to muons and all the rest were not on the horizon of people, I don't know. But somehow, I guess it's in the atmosphere right now. So people started looking at the muon couplings to axions, so the supernova bounds. So 2 papers came after us that did a much better job. Now they really see they had the MPI people simulate the supernova profiles. The off-diagonal ones, yes, this was definitely somehow. Okay, so I guess the history people know much better than I do, but my understanding is that the K2 pi A was the first killer of the original axion, the weak scale axion. So it was definitely there, and K2 pi is absolutely a classic observable that everybody knew about, I guess. Why not everything else? I don't know. This I don't know. I mean, partially is that it's in, you know, if you write the simplest models, you would not even have flavor violation.
Right.
As I had some people complaining in the beginning.
And in the neutral sector for K-longs, I guess you also have similar signatures. Yeah,
so that's another thing, no? So you're an expert, no? Well, the Koto anomaly, no? So Koto anomaly, you could also.
I was vaguely getting at that.
Yeah, I mean, yeah, if you, that's, I guess probably, I don't know, maybe it's also related to that. No? So if you have K long goes to like 2 hidden sector states, they could be, you could think of them as ALPs, or one of them as an ALP, and this ALP decays to 2 photons, you would pick it up in Koto. But there would be an SD, coupling. So somehow you mix into this sector. You could think of it as mixing into an ARP or directly into these 2 guys. Or I mean, there were many models on the market. We wrote some. You guys had more. So yeah. I don't know. Is this what you were aiming for, Jen?
Yeah, thanks for the. I was just a little, little bit puzzled at why we haven't heard many. Of course, the discussion is very complex, and you did some very heroic work in discussing all those flavor constraints. Yeah.
Yeah. I mean, the other question is, I mean, can you see something interesting? And I think that was maybe the most exciting thing was going bottom up.
Yeah. Actually, the related question is often when in the ALP discussion, people have two sets of assumptions on this fermionic couplings, right? One is they are of the same order as the GG2 FFU coupling. The other one is they are further one loop suppressed. There seems to be a lot of freedom there. And also people often assume the CP is only violated by this, our standard model part, not by the Axion interactions with the fermions. That looks into a particular linear combination of your vector current and axial vector current, right? By going away from there, one should expect something more violent or big observables in low energies, or it's just that this common assumption was just really by convenience that people assume there's no CP violation in the additional CP violation in the Axion fermion couplings.
Yeah. So well, I don't think there's really anything violent that will happen.
Yeah, because from your discussion, there's nothing violent, right? So it's so I was wondering where this common assumption come from. Maybe it's just a theoretical bias for simplicity inherited from old literature. But I will.
Yeah, I mean, so as soon as you, I mean, if you take this usual sort of anything that is allowed, you write down approach, like an EFT approach to, then if you will have a model where you have a non-universal coupling, so that you'll end up with flavor violation, you almost inevitably will have CP violating couplings.
Sure.
Right. But from the experimental point of view, okay. Yeah, I mean, I can go back, but you see this V versus A structure can really change. There were many examples,
Yeah. Your summary
can change quite significantly what you're probing. You're right. Yeah. So okay, I don't have anything more intelligent to say. I think
just some curiosity. But your study already showed. Seems like the vector current coupling receive much stronger constraints from low energy observables compared to the axial vector ones, at least as the current limit, right?
Yeah, that's for the quarks. For the leptons, it's actually a different story because you have to compare V minus A versus V plus A because of this the way this I mean, it's really just mu to A transition. The way this UDDIO, which is the most sensitive experiment at present, was designed. It was designed to be sensitive to right-handed couplings. So if you have either just vector or just axial, you're sensitive to the equal extent to the vector and axial. But if you have a left-handed, then you're much less sensitive. I had this.
Yeah, I remember that.
Remember this now. So it was, you can't see my pointer, but it's these green lines, the dashed lines above or below the solid line. So the one above is the right-handed, the one below the green line is the left-handed.
Yeah. Thanks.
Can you do anything with these experimental proposals for MEGII scattering? Like muon, I think there's one that CERN proposed.
You mean for the light by light, the HPV? Let me see, the hadronic vacuum polarization.
Yeah, that's what they want to measure, but I wonder if you can repurpose somehow.
I don't think so. It sounds to me like the number of muons involved would be. Okay, I don't know. That's the proper ways. I don't know.
Mm-hmm.
What I know is for the mu to E conversion, right?
Mm-hmm.
Which has, I mean, these guys will have the most muons. There is, it's very non-trivial, no? Because mu to E, they have to cut on the positron energy just to be able to take the data. They have so many muons. And then it depends. So if you look at the mu to EA, it's a decay in orbit. So if muon was at rest, it would be at roughly half of the muon mass. Mu to E conversion is at, it has an endpoint at the muon mass, so quite far off. But since it's a decay in orbit, you will have a leak in of the mu to EA signal into the signal region for mu to E conversion. But of course, you also have a leak in of mu to E nu bar decay in orbit. And the shapes are not the same, so that's where you can gain. There is a there's a promise for the snowmass that there will be a study. What's out there is very naive, no? And we'll see. Okay, is not. It looks tough, so it's not clear that it can do. Even though we have more muons, it's not by far not clear that you can do better than. And yeah. For this certain thing, I'm not sure. I haven't thought about it.
Yeah, it's unclear what the signature would be because, yeah.
Mm-hmm.
Well, okay. Do we have any more questions? I'll stop recording.